1.7 million people watched this Stanford lecture. Most walked away thinking they understood how ChatGPT is built. They don't, because they focused on the wrong layer. The speaker, Yann Dubois, Stanford PhD, creator of Alpaca, the model that kicked off the open source LLM wave. Today, he leads post training at OpenAI, the team responsible for making O3 and GPT-5 actually useful. And in 97 minutes, he said something most AI courses won't tell you. The architecture, the transformer everyone obsesses over, is maybe 10% of the job. The other 90%? That's what this video is about. Full lecture, linked below. Let's establish why this matters. Jan studied bioengineering at EPFL in Switzerland, then machine learning at Cambridge, then a PhD at Stanford under Percy Liang, one of the most respected names in AI research. During that PhD, he created Alpaca, a fine tuned LLaMA model that proved you could build a ChatGPT competitor for under $200. He also built AlpacaEval Konmu, the benchmark framework the entire industry now uses to compare language models. After Stanford, OpenAI hired him to lead their post training frontiers team. The people who take a raw model and turn it into the thing you actually talk to. When this person says, "Here's what matters," you listen. Yann breaks LLM development into 5 pillars: architecture, training algorithm, data, evaluation, and systems optimization. Most courses spend 80% of their time on pillar 1, architecture. Yann spends maybe 5 minutes on it. Quote, "There are already many great videos on transformers. The real differentiators, the things that separate a toy model from ChatGPT, live in pillars 3 through 5: data, evaluation, systems. Let's walk through each one. This is where models are won or lost. Not in the lab, in the data pipeline. It starts with Common Crawl, 250 billion web pages, about 1 petabyte of raw HTML. But raw data is useless. Yann walks through a 7-step pipeline to turn internet garbage into training gold. Step 1: strip the HTML tags and extract clean text. Step 2: filter out harmful content. NSFW material, personal information, toxic language. Step 3: deduplicate, remove repeated headers, footers, identical pages. The internet copies itself constantly. Step 4: heuristic filtering, rule based quality checks. If the token distribution looks weird, if the text is too short, if it's mostly boilerplate, cut it. Step 5, and this is the clever one: train a classifier to predict whether a page would be cited by Wikipedia. Pages that pass this filter tend to be high quality. Step 6: balance your domains. You don't want 80% Reddit and 2% textbooks. Upsample code, upsample books, downsample entertainment. Step 7: so fine tune on curated sources like Wikipedia with a lower learning rate. After all 7 steps, you go from a petabyte of noise to about 80 terabytes of clean tokens. Modern models train on up to 15 trillion tokens. That's the scale. Before you can train, you need to convert text into numbers. That's the tokenizer. And Yann explains why words don't work. Misspellings break word based systems. Rare words explode your vocabulary. Multilingual text is impossible. The solution: byte pair encoding, BPE. Start with individual characters. Find the most common pair. Merge them into a new token. Repeat thousands of times. The result: a vocabulary of around 50,000 tokens, each representing roughly 3 to 4 characters. It handles typos, rare words, code, emoji, and 60 languages, all with the same vocabulary. This is what GPT, Claude, and every major model uses. Simple algorithm, massive impact. Here's where theory meets money. LLaMA 3, Meta's 400 billion parameter model. Total training cost approximately $75 million. 52 million in GPU compute alone. 25 million in engineering salaries. And it emits around 4,000 tons of CO2 a year, roughly equivalent to 800 cars driving for a year. The training itself is next token prediction. Give the model a sequence of tokens. Ask it to predict the next one. Compare that prediction to reality. Update the weights. Do that 15 trillion times. But making that work at scale requires systems tricks. Low precision training. Running calculations in 16-bit or even 8-bit floating point to halve your memory. Operator fusion. Combining sequential GPU operations into single kernels to reduce data movement. And scaling laws. Chinchilla showed the optimal ratio is about 20 tokens per parameter for training efficiency and 150 for inference optimization. Tune on small models first. Fit the curve, extrapolate. Spend 90% of your budget on the final run. You've trained a base model. It can predict the next token, but it can't follow instructions. It can't have a conversation. It doesn't know. It shouldn't help you build a bomb. This is where alignment comes in. Step 1: Supervised Fine Tuning, SFT. Human experts write example conversations. When someone asks this, respond like that. The LLaMA paper showed something shocking. Just 2,000 high quality examples can transform a base model's behavior. It's not teaching new knowledge, it's teaching style. How to respond, not what to know. But SFT has a ceiling and it introduces hallucinations. The model learns to sound confident even when it's guessing. Step 2: RLHF, Reinforcement Learning from Human Feedback. Show the model's outputs to humans. They rank which response is better. Train a reward model on those preferences. Then fine tune the LLM to maximize that reward using PPO, proximal policy optimization. It works, but it's complex and expensive. Step 3: DPO, Direct Preference Optimization. Yann's simpler alternative. Skip the reward model. Use standard supervised learning to make the model prefer better responses directly. Comparable performance, a fraction of the complexity. This is the pipeline that turns a next token predictor into ChatGPT. How do you know if your model is good? This is harder than you think. Yann flags 3 major problems. First, prompt sensitivity. Pre-trained models aren't instruction followers. Change the wording of your question slightly, and the score changes dramatically. Second, data contamination. If your test questions leaked into the training data, and at 15 trillion tokens they probably did, your benchmark is meaningless. Third, metric inconsistency. Every lab uses different prompts, different few shot settings, different scoring. The benchmarks themselves. MMLU covers 57 tasks from law to medicine to ethics. Helm tests bias, fairness, toxicity, calibration. But the gold standard today, chatbot arena. Real humans rating blind side by side responses. And AlpacaEval, which Yann himself built, an LLM based evaluator that correlates 98% with human judges at a 50th of the cost. Evaluation is the unsexy pillar. It's also the one most teams get wrong. Here's what 97 minutes boils down to: the transformer architecture matters, but it's table stakes. Everyone uses roughly the same one. The real competitive advantages are messy, boring, and unglamorous. A 7 step data pipeline that turns a petabyte of garbage into 80 terabytes of signal. A tokenizer that handles 60 languages in 50,000 tokens. An alignment stack, SFT, then RLHF or DPO, that teaches behavior, not knowledge. An evaluation framework that actually catches your model lying, and the systems engineering to do all of it at $75 million scale. Yann said it best. In industry, it's data, evaluation, and systems that make or break a model. Full source Stanford CS229 guest lecture by Yann Dubois. 97 minutes, 1.7 million views. Link in the description. Comment LLM below, and I'll send you the free LLM Builders Playbook PDF. All 5 pillars, the 7 step data pipeline, and the full alignment stack on one page. Bite size AI drops on Instagram. Deep dives here on YouTube. Subscribe early. Win early.